All right, so today's video is going to be about optimal transport, and it's a really cool and fascinating topic, not just in AI, but in mathematics in general. So, KL divergence only takes you so far when it comes to measuring the similarity between distributions, right? So, we'll look at examples, real world examples, and then we'll look at how it translates into the math and all the complex and cool stuff, right? So let's say we have two distributions, P and Q, as you can see on the screen, and they have mu and a certain sigma, right? A mean and standard deviation. So how do we measure the relationship between these two distributions, right? And note that I said relationship and not just overlapping. This is where this topic becomes interesting. If you use KL divergence, and that's probably the first intuitive thing that comes to any deep learning practitioner's mind, you will face a problem when the distributions are not overlapping. So here we can see the distributions are overlapping in the first case. And when we plug in the mu and sigma values into the KL divergence formula, we end up with a zero point 0.5 value for KL divergence. And this is cool. It's good, but there's one problem. When the two distributions are not overlapping with each other and they're quite far apart, as in obviously these two extremities probably overlap at some extent, but we don't consider that. So technically, even if you look at the formula, we have mu1 minus mu2 whole square, and we have sigma 2 here, right? So in two cases, that is, if either mu1 is extremely higher than mu2, or if mu2 is extremely higher than mu1, or if sigma 2 is 0, that is, there's no uncertainty for the second distribution. In both cases, the KL divergence tends to infinity, and infinity does not really mean anything, right? Infinity is just a really huge number. So you cannot really compare between two infinities and things like, I mean, you can, it's a huge field of mathematics, but in general terms, you can't compare between two infinities, right? So let's start this discussion with a very simple and intuitive concept. So we have a pile of sand, and we want to convert this pile of sand into a different pile of sand, a pile of sand that is of a different shape, right? So here you can see this pile of sand is more like a heap, and this is more like just a flat, spread out uh, uh, sand, right? Now, how do we do this, right? I mean, obviously, in real life, it's very straightforward, but how do we do this in the most optimal way, right? Let's define what optimality is first. If we have a heap of sand, we'll have to pick a grain and drop a grain from the source to the target, where the source gets transformed into the target eventually, right? And that's what you're trying to do. The optimal way of doing this is where we are not moving too much sand, and we are not moving each grain too far, right? So both of these things need to have a certain cost associated with it, so that we don't, you know, uh, overdo it, right? So optimal transport finds the minimum cost of performing this transformation. So if you want to go from one distribution to another distribution, optimal transport is what finds the most optimal and the minimum cost path that lets us do this, right? We can look at the math. So, the famous mathematician Cantorowicz formulated optimal transport in both its primal and dual forms. But before we do that, let's look at a real life scenario, right? And let's see what's even happening so that the math and the notation makes sense, right? One disclaimer I want to give before we do anything is that we're dealing with distributions where mass is conserved, and we're not trying to talk about distributions where the mass is not conserved. For example, let's say we have an initial distribution of mass, let's say 2 metric units. We will make sure that the target distribution is also of the same mass. That keeps things a little simpler. And of course, there's a huge field of study for decaying transport. But anyway, we'll be looking at the simple case for now. So let's take a very simple case where we have three uh, sand particles, each of 1/3 units. We can take kg, gram, anything, right? Gram is probably more appropriate. So we have one sand particle at x equals 2, one at x equals 1, and one at x equals 0. And all three of them are 1/3 of whatever units, let's say a gram, right? Similarly, the target distribution has two sand particles, uh, one of half weight, and the other one is also of half weight. And the first one is kept at 2 and the second one is kept at 1, right? We can see that the weight is still conserved here because 3 1/3 add up to 1 and 2 halves add up to 1. So the weight remains conserved. It's just the size of the particle that changes essentially. So think of it in, if you want to think of it in a very simple way, we have 3 heaps of sand on one side and we have 2 holes on the other side. And we want to use these 3 heaps of sand to fill the 2 holes that we have on the other side, right? And how do we do this is what forms the base of optimal transport. How do we do this in the most optimal way, right? And you can see I've just laid out one very simple coupling plan on the screen. The interesting part about this is that there are infinite number of ways of doing this, right? But I've just put down one plan, one very intuitive plan that we can use. So let's say x1 does not go to y1. So this is x1 and this is x1 and this is y1. X1 does not go to y1 and the entirety of x1 goes to y2, right? Here. Then x2, so this becomes entirely, so this pile of sand is lifted and entirely dumped into 2, right? Now, x2 does the opposite, right? So x2 is this one where we take the entire thing and we dump it here, right? So we take the pile of sand from here and then we dump it here, right? When it comes to x3, we take half of it and we dump it here and we take the other half and dump it here. So this basically is one transport path that we can take to go from our initial distribution to our final distribution, right? There are infinitely many paths where we can take half from the other one, we can take full from, and we can have multiple permutations and combinations of this. There are 2 constraints that we need to follow while doing this. These are the marginal constraints in probability terms, but in our very simplified world of sand and holes, it is just a row sum must be equal to the source masses, right? So if we see the sum of this row is 1 by 3, the sum of this row is 1 by 3, and the sum of this row is also 1 by 3, right? So the source mass of x3 is 1 by 3, x2 is 1 by 3, and x1 is 1 by 3. So that remains conserved, and that is a marginal constraint. Similarly, for y1, it's the same thing. If you sum up this entire column, you get half. And if you sum up this entire column, you get half. So the marginal constraints need to be satisfied by any coupling plan that we create, right? And there are many such coupling plans that you can create. So this is one coupling plan gamma. Just keep a track of the notation and the words I'm using because we'll connect it back when we look at the mathematical part of it, right? So this is one coupling plan gamma, and there are infinitely many other coupling plans. So the set of all these coupling plans that we can create, set of all valid gammas, is what creates pi. And pi is just a set essentially, right? So the optimal transport problem finds the one gamma whose total transport cost is minimized, right? So each transport plan gamma will come with a cost, and we'll have to minimize the cost and we'll find the most optimal coupling plan that does this transport, right? Now, what is cost is a natural question that can come up. In our situation, we can just think of it, we can just use a simple Euclidean distance, a first order Euclidean distance, which just to keep things simple, right? So if we want to go from x equals 0 to x equals 1, then the cost would be 1 minus 0, that's 1. If you want to go from x equals 0 to x equals 2, then the cost is 2 because 2 minus 0 is 2. And similarly for 1, right? Essentially, if you want to go to 1, 2 minus 1 is 1. So what we can do is we can create a table, a cost table like this, just like how we created an optimal transport plan table. And this table essentially shows us the cost of moving x1 to y1, x1 to y2, x2 to y1, x2 to y2, and so on and so forth, right? So the idea is if you're lifting the pile of dirt and putting it into a hole, it tells you the cost of doing that, right? Now, so we have 2 things that we have right now. One is the plan and one is the cost, right? These two work together, right? Because each plan would have to be multiplied with its cost. Only then we get the, for the lack of a better term, the efficiency of a transport plan, right? And we want to find the most efficient transport plan where we optimize this and we also optimize for this. So we optimize for both the plan and the cost. So this is what happens. The optimal OT plan essentially minimizes the total cost, and the total cost is just a cumulative product of the mass that needs to be transported according to the coupling plan and the cost of this transport, right? Now, this is a very intuitive way of talking about it. Essentially, we are talking about a discrete scenario, right? This is not even a continuous scenario. It's not even a continuous distribution. It's a discrete distribution, and mass is conserved and things like that. Let's look at the whole thing from a mathematical point of view, just so that we understand the notation and understand what we are really trying to do here, right? So let's say we have two distributions, mu and v. Now, you can call this eta, whatever you want, right? It doesn't really matter. Now, we want to transform this distribution into this distribution, right? Because and both of them are live in the same space called x, right? X is the coordinate space where it lives in. How do we transport mass from mu to make v? We need a transport plan for every x that belongs inside mu to every y that belongs inside v, right? So everything, we need a coupling plan that decides each element in the distribution of mu needs to be mapped to an element in the distribution of v. And we'll consider x for all the elements in mu and y for all the elements in v. In mathematical terms, this is a joint distribution gamma for every x and y, right? Because we are creating a distribution that's coupled, right, for x and y. So this is what we are trying to do is a joint distribution gamma with the marginal constraints which I talked about over here, right? Because we need to preserve the mass. So the uh, preservation of mass is what turns, in mathematical terms, becomes a marginal constraint, right? So this is what happens here. We essentially are trying to find a coupling plan which follows this constraint. And this just means that all of mass is conserved. And this marginal constraint is what makes the coupling joint distribution, the coupling plan, valid in some sense. So there are many joint distributions gamma that satisfy the constraint, and the collection of all is what we call pi, as we discussed before. Mathematically, pi is just a set of all gammas where marginals are mu and v, right? If you use Euclidean distance for cost, like how we used in the previous example, it's just a one norm of the distance, and the total cost is just a combination of the joint distribution across all plans and across all the costs, right? So we are essentially double integrating it across the source and the target for all coupling problems and all the costs associated to it, right? So the cost, plan, source, and target all needs to work together essentially to create a total cost, and we are trying to find the one with the lowest cost. Of course, the cool version of writing this is the expectation of cost, and we are trying to minimize the expected cost. That's the version you'll find in research papers and things like that. So we want the plan that minimizes the total cost. Now, before we go into anything else, it's very important to understand why we need to know this, right? Because transforming distributions, why is this important? Why do we care? Like, sure, it's a very cool mathematical concept, but what's the use of doing all this? Uh, all the popular flow matching, diffusion, and any of these models are just distribution manipulation models, right? Where we are going from noise to a target distribution. We initially have random noise, and we are essentially over time denoising it, and we are eventually getting to a target distribution that's a image or a video or whatever it is, right? And when we add a prompt to it, it becomes a conditional diffusion by conditional generation model. So all of that is just an optimal transport formulation where we're trying to optimally transport between a source distribution that is noise and a target distribution that is data. And we are just essentially creating the optimal transport path, or a straight, in most cases, it's a straight line where we transport it from source distribution to target distribution. So Cantor-Which primal is the simple way of defining this. This is what we have defined here as well. And that's the primal form where we are essentially trying to minimize uh, the total cost, right? Cheapest way to move mass from mu to v. And this is a very simple formulation. And the problem with that is it's very hard to compute, right? Because we have so many combinations that we need to integrate over. And it's essentially a set of linear equations in discrete terms, and in continuous terms, it's an integral over all possible values. So that's where the dual comes in. And I'm not sure how many of you would know about optimization basics, but every optimization problem can be seen as a primal and as a dual. And the primal formulation is where we minimize something, and the dual formulation is where we maximize something, right? So what happens is the primal minimizes we frame the problem in a way where we are trying to minimize something to achieve something, and the dual formulation is where we try to maximize something to achieve something. And there's a concept called as strong duality in convex optimization. And what strong duality says is that when a problem has strong duality, when a convex optimization problem has strong duality, they have the same optimal value. That means when you solve this optimization problem, you get a certain optimal value for the problem. And when you solve this optimization problem, that is maximizing something, you get a certain optimization point for that, right? And what strong duality says is that for convex problems, they are equal. The solution you get by minimizing something and the solution you get by maximizing something, they are the same solution, right? And strong duality is what essentially helps us solve these optimal problems, because solving the primal form is often extremely hard and computationally extremely expensive. So what is the dual formulation, and how can we maximize something? Because cost needs to be minimized, right? We don't want to pay more than, we don't want to give more cost, right? We want to do it at the lowest amount of cost possible. So that's where we break this problem down into two parts, right? We make this a two-player game, right? The first player corresponds to picking up a, a particle of dirt from the source distribution, and the second corresponds to dropping it in the target distribution, right? That's a layman way of explaining it, but essentially, uh, we are breaking the distribution into uh, a price for picking up something and a subsidy for delivering something, right? And um, if we explain this in very simple terms, instead of searching over all possible plans, which is a huge search space and it's a very exhaustive search space, we search over pairs of F and G, right? In optimization terms, F and G are called Lagrangian constraints in optimization problems. But for us, for now, let's keep it simple. So F is the price to pay for picking up 1 unit of mass at X, that is from the source, right? And G is the subsidy you pay for delivering 1 unit of mass at Y. So uh, we are essentially splitting this problem of transport into a two-player game of picking up and dropping it somewhere. And the constraint, ST stands for such that, is that f of x plus g of y should always be less than the cost, right? So there's a total cost of transporting a point, a particle from one place to another place, that is a Euclidean or second order Euclidean or anything. And that should not exceed the combination of picking something up and dropping something. So what we are trying to do is we are trying to change the way we are optimizing the problem, but we are maintaining the same constraint that we had in the primal, right? So the worst case, the picking up and dropping, the worst case, it should still add up to the normal cost. It should not exceed the normal cost, right? So, and we are trying to minimize this, which is just the total revenue, right? So picking up and dropping, and we are trying to maximize it. Now, in primal, we are trying to minimize that. Here, we are trying to maximize the revenue. We are trying to reframe the problem in a way where we can maximize this. Because if you maximize this value, you are essentially still getting the minimum cost for transporting, right? Because that's what the constraint does here. Primal and dual is a very interesting optimization problem, and I highly encourage anyone watching this to like go through it separately, because it is a very interesting concept. And for the cost that we are talking about, we often use something called as Weierstein distance. And Weierstein distance is is a it can be a 1 Weierstrass distance or a 2 Weierstrass distance or a p Weierstrass distance, right? And this is the formula for 1 Weierstrass distance. This is just a Euclidean norm. And this is the formula for the 2 Weierstrass distance, and so on. We can essentially calculate a p norm of this as well, right? And we can replace these costs with the values that we have. Now, let's look at some code and let's see like what's happening. So this is just the first one where we can see that KL divergence essentially saturates after a certain point and it becomes quite meaningless. And because when the distributions become too far apart, right? And Weierstrass distance always keeps growing. And it's a great metric for uh, the distance between two distributions. Now, when you do a comparison between optimal transports using different costs, you can see that the mapping often tends to become different, where you can see how this one is mapped to this one, but when you use W2 uh, as your cost, it gets mapped to the other one. It gets mapped to a different target, right? So the coupling plan which we create is, as I said, we can have many coupling plans to transport from one place to the other, but the main thing we need to do is to minimize the cost. So the metric you use for cost will often define what the most optimal transport plan is, right? And with different plans, you can get different optimizations. Now, this is a very simple 2D example of image generation. I wouldn't even call it image generation, to be fair. This is the source distribution and this is the target distribution. And we are trying to learn how we can map this to the target distribution. And this is just 2D. And in the real world, when we are trying to generate an image, let's say the image is 256 cross 256, right? So it's that many dimensions, and it's a Gaussian from that many dimensions to a target Gaussian of the same dimension. And that's where the mass conservation idea comes into play, because essentially we're mapping these many pixels which have random values to these many pixels which have a certain target distribution value to it. This is how the transport looks like. It's a straight line paths, right? A very simple optimal transport. We're using W2. So we can see how the points move over time and they go from the source distribution to the target distribution. And similarly, when we do it for the smiley, it becomes like this. The same thing in higher dimensions is what you see in flow matching. And what we're doing is a linear interpolation. It's often considered as the most efficient way of image generation, right? In diffusion and flow matching and things like that. Just a vector field diagram, because most flow matching models are just a simulation of an ODE, right? An ODE is an ordinary differential equation, and you can check that out. It's a very interesting topic. There are so many videos on YouTube about it as well, and this is just a example of what happens. But yeah, this is what I wanted to talk about today, and it definitely is a very interesting topic. Optimal transport essentially talks about how we can transform one distribution to another distribution, and how we can use this in math, how we can use this in AI, and so many applications in the real world as well. But yeah, that's about it. Peace.